cover Section 4, Part 4, Caching with CloudFront. You can write your own code to customize how your CloudFront distributions process HTTP requests and responses. The code you write and attach to your CloudFront distribution is called an edge function. The code runs close to your users to minimize latency, and you don't have to manage servers or other infrastructure. You can write code to manipulate the requests and responses that flow through CloudFront. You can also perform tasks like basic authentication and authorization or generation of HTTP responses at the edge. CloudFront provides two ways to write and manage edge functions. The first is Lambda at Edge. This extension of AWS Lambda offers powerful and flexible computing for complex functions and full application logic closer to your viewers. It is also highly secure. Lambda at Edge functions run in a Node.js or Python runtime environment. You publish them to a single AWS region. When you associate the function with a CloudFront distribution, Lambda at Edge automatically replicates your code around the world. CloudFront functions are lightweight JavaScript functions for high-scale, latency-sensitive CDN customizations. The CloudFront functions runtime environment offers sub-millisecond startup times, scales immediately to handle millions of requests per second, and is highly secure. CloudFront Functions is a native feature of CloudFront, which means you can build, test, and deploy your code entirely within CloudFront. This diagram illustrates how Lambda at Edge functions run. The white boxes highlight steps that Lambda manages, while the purple box highlights the steps CloudFront manages. When you associate the function with a CloudFront distribution, Lambda at Edge automatically replicates your code around the world. Lambda at Edge functions are run in a regional edge cache, usually in the AWS region closest to the CloudFront edge location that the client can reach. This Lambda function code demonstrates how to change the origin domain name based on the CloudFront viewer country header. In this way, content is served from an origin that is closer to the viewer's country. Using this functionality for your distribution can reduce latencies when the specified region is near to the viewer's country. It can also provide data sovereignty by making sure data is served from an origin in the same country the request came from. Similar to Lambda at Edge, CloudFront Functions runs your code in response to events that CloudFront generates. CloudFront Functions can be invoked after CloudFront receives a request from a viewer, before CloudFront forwards the response to the viewer. When you associate a CloudFront function with a CloudFront distribution, CloudFront intercepts requests and responses at CloudFront edge locations and passes them to your function. This function code redirects the viewer to a different URL and also returns a customer response header. In this example, the developer sends a request to the distribution's domain name. The function redirects them to https://aws.amazon.com/CloudFront and adds the custom response header. How do you know whether to use Lambda at Edge instead of CloudFront functions? Well, generally speaking, Lambda at Edge gives you more options and capacity to create edge functions. However, CloudFront Functions gives you a quick way to handle lightweight functions at the edge at about 1/6 the cost of Lambda at Edge, all within CloudFront. Lambda at Edge is a good choice for functions that take milliseconds or more to complete, functions that require adjustable memory or CPU, functions that depend on third-party libraries, including the AWS SDKs for integration with other AWS services, functions that require network access to use external services for processing, and functions that require file system access or access to the body of HTTP requests. CloudFront Functions is a good choice for use cases such as cache key normalization, header manipulation, header URL redirects, and request authorization. Here are the key takeaways for this section of the module. CloudFront is a fast CDN service that delivers data globally with low latency and high transfer speeds. CloudFront distributions can serve web, video, or live streaming content. A cache key is the unique identifier for each object in the cache. And you can use CloudFront Functions and Lambda at Edge to customize how your distribution processes requests and responses. That's it for this video. Thanks for watching, and I'll see you in the next video. Time to review the module and wrap up with a discussion of a practice certification exam question. In this module, you learned how to explain when caching is used, describe caching with Elasticache, describe caching with CloudFront, describe and compare Lambda at Edge and CloudFront functions, and apply caching strategies. Now let's take a look at a sample exam question. Which requirement is a reason to choose Memcached over Redis for your Elasticache configuration? A, you need data replication. B, you need the simplest model possible. C, you have complex data types. D, you need an in-memory cache. Note the key requirements stated in the problem. The answer needs to be the requirement to choose Memcached over Redis for Elasticache. Consider the answer choices and rule them out based on these key requirements. Let's pause a few seconds before discussing the correct answer. If you need more time to consider the answer choices, pause the video. So, how do these answer choices compare to the requirements? For A, Memcached doesn't support replication, so this wouldn't be a reason to choose Memcached over Redis. For B, if you need a simple model, Memcached is a better choice if you don't need the advanced features of Redis. This could be the answer. If you have complex data types, you would want to choose Redis instead of Memcached. This isn't the answer. And for the last answer choice, both engines provide an in-memory cache, so that wouldn't make you choose Memcached over Redis. The correct answer is B. Use Memcached when you want to use the simplest model possible. That concludes this module. Thanks for watching. We'll see you again in the next video.
Hello and welcome to Module 10, Developing with Messaging Services. We'll begin with Section 1, Introduction. At the end of this module, you should be able to illustrate how messaging services, including queues, pub/sub messaging, and streams, support asynchronous processing. Describe the Amazon Simple Queue Service, or Amazon SQS, and send messages to an SQS queue. You should also be able to describe the Amazon Simple Notification Service, or Amazon SNS, subscribe an SQS queue to an SNS topic, and describe how Amazon Kinesis can be used for real-time analytics. In this module, you will learn about processing requests asynchronously, Amazon SQS, working with Amazon SQS messages, and configuring Amazon SQS queues. You will also learn about Amazon SNS, developing with Amazon SNS, and Amazon Kinesis data streams. Currently, updating the coffee inventory on the website is a manual process. Sophia would like to find an easier way to keep the inventory updated. She considers setting up a messaging system to automatically receive and process inventory updates. Matteo, a cafe regular and AWS consultant, suggested using the Amazon Simple Notification Service, or Amazon SNS, to receive messages from the suppliers. He also suggested using an Amazon Simple Queue Service, or Amazon SQS, queue to store the messages until they are processed. The diagram on this slide gives an overview of the application that you will build through the labs in this course. The highlighted portions are relevant to this module. As highlighted in the diagram, you will use Amazon SQS and Amazon SNS to set up a system to receive, queue, and send the coffee inventory information. That's it for this video. Thanks for watching, and see you in the next video. This video covers Section 2, Part 1, Processing Requests Asynchronously. In a synchronous model, the client, the producer, generates a request message to the consumer. Then, the client waits until the message is processed and the client gets a response from the consumer. This is a relatively simple interaction common to create, read, update, and delete, also known as CRUD API actions. In a coffee shop, an example of synchronous processing is ordering a coffee at the counter and getting the cup of coffee immediately before you walk away. This action is complete before the next person orders. In the example diagrammed on the slide, the client makes a request to service A. Service A then calls Service B. Service A waits for Service B to complete its actions and respond back. That response then goes back to the client. In this model, strong interdependency exists between the producer and the consumer, which creates a tightly coupled system. The disadvantage of a tightly coupled system is that it's not fault tolerant. If any component of the system fails, the entire system will fail. If the consumer fails while processing a message, then the producer will be forced to wait until that message gets processed, assuming that the message is not lost. Additionally, if new consumer instances are launched to recover from a failure or keep up with an increased workload, the producer must be explicitly made aware of the new consumer instances. When a producer and consumer are tightly coupled like this, the coupling is prone to brittleness. In contrast is asynchronous processing. In this design, the client or producer sends a request and might get an acknowledgement that the event was received. However, the client doesn't receive a response that includes the results of the request. In the coffee shop example, this is like placing an order that's delivered later. You get your order number, and then the next person in line can order without waiting for your order to be fulfilled. Someone brings you the order when it's ready. A problem completing your order does not prevent the person behind you in line from ordering. In the example diagram on the slide, when the client makes a request to Service A surfaces the event to its consumer, Service B, and moves on. The disadvantage is that Service B does not have a channel to pass back results to Service A. You need to write your applications to get the results and deal with errors asynchronously. Although you might be used to writing code that has explicit coupling, the coupling is not actually needed for the type of processing you're doing. The advantage of an asynchronous approach is that you reduce the dependencies on downstream activities, and this reduction improves responsiveness back to the client. This means you don't need to put logic into your code to deal with long wait times or handle errors that might occur downstream. After your client has successfully handed off the request, you can move on. The producer doesn't need to wait for the first message to be read. Instead, the producer can continue to generate messages whether the consumer is processing them or not. The producer isn't impacted if the consumer fails to process the message. This means much less interdependency between the producer and consumer, which makes the system more loosely coupled with greater fault tolerance. That's it for this video. Thanks for watching, and see you in the next video. This video covers Section 2, Part 2, Processing Requests Asynchronously. 3 types of messaging services are available for asynchronous processing: message queues, publish-subscribe or pub/sub messaging, and data streams. The type of messaging service you choose depends on your use case. We'll look at each type over the next few slides. In each type, producers send requests or messages to a service and do not wait for a result. The messaging service provides an interim location from which consumers get messages. This provides an asynchronous, decoupled design between your components. You will learn about 3 fully managed services you can use to implement each type of messaging service: Amazon SQS for messaging queues, Amazon SNS for pub/sub messaging, and Kinesis data streams for data streams. A message queue is a temporary repository for messages waiting to be processed. Messages are usually small and can be requests, replies, error messages, or plain information. Examples include customer records, product orders, invoices, and patient records. In a message queue workflow, the first step is the producer adding a message to the queue. The message is stored in the queue until another component, a consumer, retrieves and processes the message. Second, consumers poll the queue to determine if new messages are available to process. Next, each consumer processes each new message it retrieves. If processing is successful, The consumer deletes the message from the queue so that no other consumer tries to process the same message. With publish-subscribe or pub/sub messaging, publishers or producers send messages to topics. Message topics provide a lightweight mechanism to broadcast asynchronous event notifications. Topics also provide endpoints that software components can connect to. Unlike queue consumers, subscribers do not need to check for messages in a pub/sub model. Instead, messages published to a topic are pushed out to all topic subscribers. With pub/sub messaging, you can easily notify large numbers of subscribers about events. For example, you might publish a message to an alerts topic when a certain type of error occurs, and multiple consumers might take different actions on that message. Data streams are similar to queues because they provide a temporary repository for producer messages, and consumers poll the stream to check for new messages. Streams are different from queues because the rate of messages is typically much higher. Rather than processing each individual message on the queue, streams are typically used to analyze high volumes of data in near real time. Another distinction from queues is that multiple consumers might process the same messages and do entirely different actions with them. Consumers all view the same data, similar to looking through the same window, and act on the messages for their own purposes. Consumers don't delete messages from a stream. Streams are helpful for use cases where you need to handle rapid and continuous data intake and aggregation. Here are the key takeaways for this section of the module. An asynchronous design reduces interdependencies and can improve responsiveness to the client. Messaging services are good for creating asynchronous designs and include queues, pub/sub messaging, and streams. And AWS provides fully managed messaging services, including Amazon SQS, Amazon SNS, and Kinesis data streams. That's it for this video. Thanks for watching, and see you in the next video. Introducing Amazon SQS. Amazon Simple Queue Service, or Amazon SQS, is a fully managed message queuing service. With Amazon SQS, you can decouple and scale microservices, distributed systems, and serverless applications. The service eliminates the complexity and overhead associated with managing and operating message-oriented services, so that you can focus on the business logic of your application. You can use Amazon SQS to transmit any volume of data at any level of throughput without losing messages or requiring other services to be available. With Amazon SQS, you can decouple application components so that they run and fail independently, which increases the overall fault tolerance of the system. Multiple copies of every message are stored redundantly across multiple availability zones so that they are available when they're needed. Amazon SQS uses the AWS cloud to dynamically scale based on demand. Amazon SQS scales elastically with your application so that you don't have to worry about capacity planning and pre-provisioning. The number of messages per queue is not limited. You can use Amazon SQS to exchange sensitive data between applications using server-side encryption, or SSE, to encrypt each message body. Amazon SQS SSE integration with AWS Key Management Service, or AWS KMS, provides the ability to centrally manage the keys that protect Amazon SQS messages along with keys that protect your other AWS resources. AWS KMS logs every use of your encryption keys to AWS CloudTrail to help meet your regulatory and compliance needs. Amazon SQS offers both standard and first-in, first-out, or FIFO queues to support different processing priorities. Amazon SQS supports two types of message queues. Standard queues are the default queue type. Standard queues provide best effort ordering, which ensures that messages are generally delivered in the same order that they're sent. Standard queues support at least once messaging delivery. However, occasionally more than one copy of a message might be delivered out of order. Standard queues also support a nearly unlimited number of transactions per second, or TPS, per action. First in, first out, or FIFO queues, are designed to enhance messaging between applications when the order of operations and events is critical, or where duplicates can't be tolerated. FIFO queues also provide exactly once processing, but they have a limited number of TPS. The next section provides more information about queue type distinctions. You can integrate Amazon SQS with other AWS services to make applications more reliable and scalable. This illustrates an example of using an SQS queue to decouple components in an image processing application. In this example, a user uploads a photo to an Amazon Simple Storage Service, or Amazon S3 bucket, which invokes an AWS Lambda function. The Lambda function sends a message containing information about the image to an SQS queue. A processing server that is part of an Amazon EC2 autoscaling group polls the SQS queue for messages to process. After processing the photo, the processing server sends the processed photo back to the S3 bucket. Note that the autoscaling group scales based on the size of the SQS queue. The processing servers keep working until the queue is empty and then keep holding until messages appear. If the EC2 instances become unavailable, the Lambda function can keep putting messages on the queue when an upload is made. When the autoscaling group is ready to start consuming messages again, it polls the queue for messages. That's it for this video. Thanks for watching, and see you in the next video. This video covers Section 5, Part 1, Configuring Amazon SQS Queues. Standard queues are the default queue type. Standard queues support a nearly unlimited number of transactions per second, or TPS, per action. Because of the queue's highly distributed architecture, which provides this high throughput, you need to account for two potential conditions related to message delivery to your consumers. First, messaging order is not guaranteed. Standard queues provide best effort ordering. This ensures that messages are generally delivered in the same order as they are sent, but some might be delivered out of order. If your target application needs to process the messages in the order received, you need to include logic in your consumer application to reorder messages before further processing. Second, more than one copy of a message might be delivered. Standard queues support at least once delivery, not exactly once delivery. To avoid processing the same message more than once, your application code needs to check for duplicates and only process a message the first time it's received. For example, you might add code that checks your database for a unique value in the incoming event and ignores it if it already exists in the database. Message ID is a unique identifier that Amazon SQS generates. If you want to verify the uniqueness of the record on the SQS queue, you could use the message ID attribute. Another scenario might be that you actually need to verify the uniqueness of the payload. For example, if an upstream producer sent the same record to Amazon SQS twice, each event would have a unique message ID in Amazon SQS, but would be the same payload from your application's perspective. You can avoid processing the same payload twice using the MD5 of body attribute in the Amazon SQS event. This field represents a unique hash of the payload. To avoid having to write code to handle message ordering and deduplication where order is critical and duplicates can't be tolerated, use a first in, first out, or FIFO queue. FIFO queues are designed to provide exactly once processing, which helps you to avoid sending duplicates to a queue. FIFO queues also guarantee message ordering. FIFO queues support message groups, which allow multiple ordered message groups within a single queue. FIFO queues do have a more limited TPS throughput than standard queues, so only choose a FIFO queue if you need its additional features. You can use the AWS Management Console to create and configure your SQS queues, and you might find it helpful to use the console to send test messages to your queue. You can also create and configure queues using API operations and set queue parameters similar to some of the message parameters that you just learned about. For example, you can set the wait time seconds on the queue itself rather than an individual receive message request. Let's review some of the basic queue options. Use create queue to create an SQS queue including queue attributes. With set queue attributes and get queue attributes, you can set and retrieve the attributes of a queue respectively. These options help you estimate the resources required to process Amazon SQS messages. Use get queue URL to retrieve the URL of an SQS queue. To retrieve a list of your queues, use list queues. And with delete queue, you can delete a queue, regardless of whether the queue is empty. When a queue is deleted, any messages in the queue are no longer available. This example from the AWS command line interface, or AWS CLI, creates a queue named myQueue with the parameters in the createqueue.json file. This JSON file specifies a redrive policy for failed records. The policy sends failures to a dead letter queue called myDeadLetterQueue after 1,000 attempts, also known as max receive count. The parameters file also sets the message retention period for the source queue to 259,200 seconds, which is 3 days. If a message remains on the source queue for more than 3 days, it will be discarded regardless of the max receive count. That's it for this video. Thanks for watching, and see you in the next video. This video covers Section 5, Part 2, Configuring Amazon SQS Queues. Secure your Amazon SQS resources in 3 ways. First, use identity and access management. Access to Amazon SQS requires credentials that AWS can use to authenticate your requests. These credentials must have permissions to access AWS resources such as SQS queues and messages. Use AWS Identity and Access Management, or IAM policies, and Amazon SQS policies. Amazon SQS has its own resource-based permission system, which uses policies written in the same language used for IAM policies. Therefore, you can achieve similar results with Amazon SQS policies and IAM policies, and you might use them in combination. Second, use data encryption. Encrypt your data using server-side encryption, or SSE. With SSE, you can transmit sensitive data in encrypted queues. SSE protects the contents of messages in SQS queues by using keys that are managed by the AWS Key Management Service, also known as AWS KMS. When you enable SSE on an SQS queue, Amazon SQS will encrypt an incoming message before storing it on the queue, and unencrypt it upon delivery to the consumer. The encryption occurs at a point in time and applies to messages arriving after that point. For example, if messages 1 through 10 are on the queue when you enable SSE, message 11 will be encrypted, but messages 1 through 10 will not be. Third, protect inter-network traffic privacy. If you use Amazon Virtual Private Cloud, also known as Amazon VPC, to host your AWS resources, you can establish a connection between your VPC and Amazon SQS. You can use this connection to send messages to your SQS queues without crossing the public internet. In this example, the IAM policy and Amazon SQS policy grant equivalent access to a user named Bob, who is in the account where the SQS queue exists. The IAM policy grants the permissions to use the Amazon SQS receive message and send message actions for the queue called myQueue in the AWS account. The policy is attached to Bob. The Amazon SQS policy also gives permissions to Bob to use the receive message and send message actions for the same queue. Here are the key takeaways for this section of the module. Standard queues provide nearly unlimited throughput, but don't preserve message order and might include duplicate messages. FIFO queues preserve order and provide exactly once delivery, but have more limited throughput. And queue security includes managing access to queue resources, protecting data stored in the queue, and limiting exposure of messages to the internet.